Hi everyone, my name is Mark and I'm a machine learning engineer in Pinsight. And today I will talk about few-shot learning, few-shot object detection related to detecting utility poles from Google Street View images. Okay, let's go. So firstly, let me introduce these guys. They are Wireless 2020, and with this company we have made this project possible. So Wireless 2020 is a New York-based fiber, wireless, and mobile broadband consulting company that is consulting companies all over from the world. And as you understand, we'll talk a lot about like this wiring, fiber cables, and other stuff. So firstly, let me introduce a couple of variables, couple of like key points that will help us understand this project better. So first of all, usually the wiring of kind of electricity wiring, TV communication, internet, and other stuff is happening in two ways. First one in the left picture is the way of supplying wires through the underground. So what they do is they dig up some holes over there, they put wires there, and with that approach they supply like towns with electricity and stuff. And the next approach is having these utility poles. Everyone has seen one in the streets, this in the right picture, and putting wires on the utilities. And with these poles, the electricity and other telecommunication cables and other stuff goes to towns and cities. And you can imagine that doing everything for the underground case, it will be much more expensive and much more time consuming, because every time if you want to supply new wires, you need to dig up those places and put everything there. And for the second case, you just go, there's a utility pole already installed, you just put your wirings on top of it, and it's much faster and less costly. Let us also understand one more thing. So there are mainly two types of utility poles out there. So first one is like T-poles. They're called T because like obviously they're T-shaped. They have these T-hands. And also S-poles. S-pole stands for like straight poles. They are kind of have similar activity as T-poles. They're just missing the T-shaped shape. So what the companies and what wireless is providing service for with its WireGeo platform is, let us introduce a telecommunication company, Vivline.com, let's say. So Vivline.com wants to expand into another market and wants to apply supply wiring to these locations. So it has two kind of opportunities for expansion, to location A and location B. So what's wireless doing is it is providing this telecommunication company information that location A has, all of these streets has like 20% of RL wiring, which means that only 20% of the streets have these utility poles. And location B has 75% utility poles wiring, RL wiring. And based on this information, this telecommunication company might decide to do expansion on location B because there are already utility poles there and it is less costly to apply new wiring and do its businesses there. So this is the main idea of their project, and how they come up with these percentages and stuff. So the manual process that was wireless doing is they have this kind of Google Maps kind of files. They are called KML files. And you can see like the red lines over the streets. So for each red line, they have like the coordinates of latitude and longitude of the specific location. And what they are doing is they are going through each point and they are like looking through Google Street View, Google Earth, and manually, like a person is going and doing all stuff, they check whether there are utility poles installed there. And if there's a utility pole there, they start to segment those areas. So if there are utility poles, those streets are considered as RL wired. And if utility poles are not present there, it is considered like underground wiring. And with doing this, they have information of the percentages of that specific town having aerial or underground wiring. And for the red ones is like the places where street view is not available, or it is quite difficult to see whether there is pole installed or not. I mean, it might be under the, like in the back of trees and stuff. Okay, so what we've done is we automated this whole process. Firstly, what's our approach doing is we connect to Google Street View API. From this API, we get like the images for each specific point that we had in the KML file, and we download like 4 pictures from them, front view, back, right, and left. And then we construct a simple object detection model through which we check from these all images whether there's a utility pole there or not. So after that, we construct the KML file with all the information of kilometer distances of this wiring, and similar to this file, we get the output of the segmentation in the streets. Now, this is the whole process, but during this talk, we'll concentrate on how we build this object detection model that is detecting utility poles from the images. First of all, let's talk about the data. We are given like data of 2,500 T-poles, annotated data, and that's it. We have just that amount of images and they're annotated. What we can do, we just build the object detection model, which is detecting the T-poles. However, there's a huge problem in here. It turns out that in all our locations, around the 50% of the poles that are present there are S-poles. So if we build just a model that is detecting T-poles, we'll miss 50% of the locations that are have S-poles installed. And now we need to somehow solve the problem of the detection of S-poles. One of the possible solutions to do this is that first comes to mind is we just collect more data about the S-poles, we annotate it and continue training our object detection model similar to T-poles. However, I mean, this process is coming to first mind, but it's very not cool and very time consuming and costly, because imagine you need to download all of these S-pole images, you need to hire people to do all these annotations, then check whether they are doing annotations good enough, because models are heavily reliant on that. And also the worst thing is you just need to sit down and wait when these annotations are done in order to start modeling. So it is a long process and you don't want to undergo through it. And the solution of it is using few-shot object detection. What is during that, we only need 5 to 10 annotated images of our for S-poles, and only having that amount of annotated images, we will be able to construct a model that will also detect that kind of poles. Okay, now I will talk about a little bit few-shot learning. We'll dive deep into few-shot classification, and then talk a lot about few-shot object detection. So firstly, let's define few-shot learning is the task of solving a machine learning problem with only having limited amount of annotated data. And we want to define the simple few-shot classification problem. So here we have n-way k-shot classification problem, and we have a support set that consists of n classes labels, and for each class we have k labeled images. Also we have q query images, and we want to classify the query images among these n classes. So this is the problem statement that we want to solve with few-shot image classification. To be more visual, to understand more visual in a visual sense. So here, like we have three-way two-shot classification problem, because we have like 3 classes, and for each class, like we have 2 images in there. And the query set is like images that are corresponding to any class from the support set. So basically, these are the visuals of few-shot classification problem. Now I'm talking about some support set and query set. Let's also define what are those in order to get the full picture of here. So for few-shot learning, we have like mainly three types of sets. So first one is the base set. Base set is like the big training data with annotated images of base classes. So in our case, the base classes are tuples. We have 2,500 annotated images of tuples. Then we have the support set, which are the few samples of novel classes or support classes. They are called in both ways. And with these classes, we want to fine-tune our model to detect it. So in our case, it is the S-pulse, and the query set is the set to evaluate our model on our fine-tuned model. And in this case, the set also consists of S-pulse. Okay, so for the few-shot classification, there are mainly a couple of ways of doing. So I will talk about two of them, meta-learning and metric learning. During the meta-learning, here is what's happening there in the image. We have like two stages. First thing is meta-training, and the second part is meta-testing. During the meta-training, we initialize a meta model, and we take from base set kind of images and construct it in a way that is similar to meta testing, the support set and query. So we have these kind of episodes. Inside of them, it is like firstly sets, few shot sets similar to support set and the query set. And the training happening in a way that firstly it starts training the base model in an episodic way. After each episode, it starts to fine-tune the model on meta testing on a support set. And in the end, the classification loss of the query images is backpropagated for the meta model. So in this way, the overall meta model learns to clearly to initialize parameters in a way that, given like few examples, it would be able to quickly understand what classes it belong and transfer it to the query set. And the other approach is the metric learning. All these networks is quite similar to Siamese networks. So for the matching networks, after having base model trained on a base set, we just calculate the embeddings of support set and query set images and start to calculate like the distance metric between them and whichever like cosine similarity metric, and whichever class is more similar from query to support set, we classify it to belonging to that class. For the prototypical networks, the process is the same. The only difference is that whenever they calculate the embeddings, they average this embedding across the support classes and then compare with query images these averaged embeddings with the same distance metric. And for the relational networks, everything is the same. However, they get rid of this cosine similarity distance metric and let the model itself train its distance metric, and during the training model itself understand what things to compare in what way. And that is it about few-shot classification. Now we come to the few-shot object detection, and firstly it is important to key out all of the differences between few-shot object detection and few-shot classification. So firstly, and the most important difference is that we have several objects per image. During the few-shot classification case, for each image, like we have only one object in that image, and we want to classify that specific image having any class from the support set. And in this case, we can have multiple objects as object detection class, multiple objects in a single image. And the important thing is that we can have both the base classes and novel classes in the same image. Like in this picture, our base classes are bicycles and novel or support classes are humans there. So we can have images that contain both bicycle and humans in them, and it's important during the base training to remove the annotations of people from the data, then start training. However, we don't need to get rid of the images that contain human. We use them during base training. However, we remove only annotations there. The second point is joint prediction on base and novel classes. What this means is that during few-shot classification, usually they make evaluation on novel classes only. They train the base model, however, after fine-tuning, the evaluation is done only on novel classes. For few-shot object detection, the evaluation is done both on novel and base classes. And the idea is that we help the model during evaluation not to forget information about the base classes that it learned during base training. And so after fine-tuning, the model contains both information for the base classes and novel classes. And if there's an image that contains these two classes, we will not like forgetting anything about the base ones. And we are detecting both people and bicycles in the image. And the last thing is learning to learn. We see fine-tuning. As you remember, during few-shot classification, episode-like learning was used. So from the base set, we constructed the episode similar to the support set and query set, and then trained for each episode after fine-tuned on a support set and evaluation on query set. During few-shot object detection, it is not done in this episodic learning way. Firstly, they fine-tune the whole few-shot object detector base model on the whole base classes, and then firstly train on base classes, and then they fine-tune it only support set for once, and later they give evaluation for both base classes and support classes. These are the key three differences between few-shot object detection and classification. There are like many more, but these are the ones that we need to consider for sure. And already we came to the point of what approach I used for solving this problem. It is called frustratingly simple few-shot object detection. It used the two-stage fine-tuning approach. As you can see, there are two stages, the base training and few-shot fine-tuning. During the base training, as I already mentioned, the model, initiated model, which in our case is faster RCNN, is trained on the base training data set fully. With this training, we help the model to learn how to extract good features from the images, from which we'll later use this feature extractor part in the fine-tuning stage. And for the second stage, as you can see, the blue shaded area here is our feature extractor. We freeze the feature extractor during fine-tuning, and we randomly initialize weights for box classifier and box regressor and start to fine-tune on the support set. So to sum up this part, we do the base training on the base model on base classes. We fix the feature extractor and initialize new weights for box classifier, box regressor, and do the fine-tuning on the support set. It is quite simple, hence the name frustratingly simple few-shot object detector. So key takeaways from this paper were that they wanted to achieve the separation between the feature representation learning and box detector learning. That's why it is kind of two-stage process, and they achieve it with doing this kind of training. During the fine-tuning, they lowered the learning rate around 20 times, so the model converges on the support set better. And it is interesting, the training data feeding approach. They describe that in order to have a better fine-tuning, it is beneficial to use images that contain both base and support classes in the same image. In that way, model better understands the differentiation factor between the base classes and novel classes. So whenever we are doing fine-tuning for 10 or 5 shots, we need to make sure that there are two classes, in our case the T-pulse and S-pulse, present in the same image. Okay, now let us see the results of doing this training on 10 shots only, meaning we have just 10 images for the of annotations of S-poles. So the left picture contains prediction of base training. After the base training on T-poles, a model only identifies the T-poles. And after 10-shot fine-tuning, we see that model is capable of understanding that there are also S-poles in the same picture. Here's another result there. Left one is base model, and right one is fine-tuned model. And also one more example. And basically with this, I end up we kind of solve our problem of detecting what kind of poles available. A couple of words about the deployment. So we used Google Compute Engine to deploy this model into the production. We took a virtual machine with the specific specifications, and we used the NVIDIA Tesla T4 GPU for the inference in production. And it was around monthly $260 cost if it's constantly running in the cloud. What are the other plans that we can use to solve these problems or for future works? First of all, it's quite important the selection of shots. Many papers say that one of the important things here is the selection of training data set, is the correct augmentation and other stuff. So here we can achieve better results if we choose different shots there. We need to kind of handpick better images with better positions of, in our case, poles, so both to have T-poles and S-poles in the same image. So selection of data is very important in this kind of meta-learning and few-shot detection cases. And the other approach is using like self-supervised approaches such as DETREG. What is the main difference is that during the base training, in this case, we don't even have annotations for the base classes. So we have just images of, I don't know, a lot of images of T-poles and S-poles, but we don't have annotations. And these models help to kind of get features from these images using self-supervised approaches. And only after that, we get like a couple of annotated images for both base classes and novel classes. In our case, both are becoming like novel classes, and we only fine-tune with them. So firstly, train the base model with self-supervised approach, and then only fine-tune with the novel classes there. Okay, basically, this is what I plan to talk about today. So thank you for coming. If you have any questions, you are welcome. And you can find me in LinkedIn here.
Thank you for presentation. I have a question about fine-tuning. What model do you use for fine-tuning?
Okay, so for the object detection, faster RCNN is used both for base training and fine-tuning. And this first part here of the faster RCNN is frozen for the fine-tuning stage. And box detectors, classifier and regressor are randomly initialized and then fine-tuned.
Okay, thank you. And second question, in few-shot learning, few-shot object detection, in generally, what is the percentage of labeled data, or like you say 5-10, but what is the overall amount of data, like 10,000s, or what is typical amount of labeled data?
Okay, thank you for the question. Usually when we talk about few-shot learning, we just mean having 1, 2, 3, 5, and up to 10 labels. And if you have like 10,000 of images of annotations, then it most definitely will work better than just 10 shots. But in real life scenarios, usually we don't have that kind of. So the precise answer is if you have a lot of data, then do like the normal training, it would get for sure better results. But in case of small amounts, then you apply few-shot learning.
Okay, thank you.
Thank you. Thank you for your very interesting speech. And my question is, the usual practice tell us if you have very small amount of data, use augmentation. Did you use augmentation?
In our specific case, no, but yeah, I was talking about that over here, that selection of shots and augmentation is quite important in this case, in overall cases. All of the papers say that in case of missing data, augmenting it and having multiple of them, it would be help. But in this case, we don't do any specific augmentation here. The thing is, I tried with this and it gave like okay results, and I didn't go further for the augmentation.
There is no specific reason, you just keep this for the future.
Yeah.